ahead and get this going. So Ohm's law. So let's see what y'all remember. What is an electric circuit? What are the three things that make a circuit? Source, path, load. And that is actually true for any circuit you ever create. You have to have a source. There has to be some place where all things originate. You have to have a path to get whatever you're trying to move from one place to another. And then you have to have a load. You have to have something that does the work. That applies for every circuit in the world. I don't care if it's hydraulics, pneumatics, electrical, or even if you're just driving somewhere. You have a source, you have your home. You have the path, that's the road. And you have the load, your car. Now that's something to think about. Okay. What are the components of a basic circuit? We already talked about that. What other devices are probably a part of a basic circuit? We'll talk about that. What is the function of a voltage source? Okay. What does voltage even do? What is voltage, period? Voltage, and the whole purpose of voltage is it's the push. It's the initial need. Okay? So think of it as you dump a bunch of water upstream in a river. That's voltage. That's going to push everything else downstream. Does that make sense? What is the function of a conductor? It's a path for things to travel on, yes. And then what is a load? Huh? The more accurate way to say that would be that a load is something that does work. Okay? Like a motor, a light bulb. What does a light bulb do that's work? It produces light. Right? What does a motor do? It produces motion. So that's the whole purpose of a load, is to produce some form of work. I don't know if we kind of went over in depth what the difference between a closed circuit and an open circuit. We're going to really get into depth with it on this particular subject. So let's kind of talk about who knows what's the difference between a closed circuit and an open circuit?
Open circuit is a closed light switch, a closed circuit. So when the circuit's open, we can't have anything traveling through it. But when the circuit is closed, it's a complete path for the current traveling.
It's the same. You're trying to do it the opposite way there, but what it is a closed circuit is one that is in operation. An open circuit is not in operation. So how many of you have ever seen the bridges that they use that can pull themselves up and down to let ships through? Y'all know what I'm talking about?
It's the ones that like near water.
Well, it's across most of like big open spaces of water. All right, so if we have a bridge, okay, suspension wires and all, a couple more pylons here. That's not too bad a bridge. Okay, So something like that is what we're kind of looking at here. So the suspension bridges, you know what I'm talking about. They're the ones that you let a boat through because guess what? You needed boats to go up into the canal, right? So you have two types of bridges. Or you have this one type of bridge. So whenever the bridge is closed, right? Whenever it's in this state, all the cars can do what? They can drive through, right? Whenever it's open like this, where are all the cars? They're sitting on either side of the bridge, right? They're waiting for that bridge to close. That is the difference between an open and a closed circuit. An open circuit, you're going to have no traffic flow, right? No current flow. Everything sits still. On the closed bridge, everything moves through. Does that make sense? Now, why is that important? Because whenever you're talking about any kind of circuit from here on out, we're not going to have a single load. We're going to have multiple loads. So what does that mean? Well, that means that if I have an open circuit versus closed circuit, or an open resistor versus a closed resistor circuit, the state of that circuit is going to impact my circuit overall. Does that make sense? All right. So let's kind of go on with all this. So an electrical circuit provides a path for current to flow. A closed circuit is a complete path. An open circuit is not. Basic circuit includes source, conductor, load, and if you're doing an electrical circuit or a hydraulic circuit, you have to have something to return the electricity or the fluid back to source. Does that make sense? A control device. Now, in a very basic circuit, we don't use a control device. Control devices are things like a light switch, fuses, circuit breakers, things like that. Now, why don't we use those in the simplest circuits? Because it's not always needed. Something like a switch is a very convenient thing to have, but is it absolutely, positively, utterly necessary? No, we don't have to have that. By the way, OCPD is the short version of Overcurrent Protection Device. So that's fuses and circuit breakers. Now, fuses and circuit breakers, again, are not absolutely necessary. If you're not going to have something that's going to draw a large bunch of current to it, you don't need anything. Current is probably the part of a circuit that is most destructive. It's the element in all of this that is the most destructive. Why? Because the more, think about it like the Mississippi River. All nice and calm, up until you jump up a bunch of water upstream and then flood out everybody downstream. Right? Okay? Does anybody remember the Mississippi River floods that happened a few years ago? Major devastation, right? It took out whole communities, flooded over the banks, and flooded miles around itself. That was the Mississippi River. It flooded really terribly back in the what? 90s or early 2000s? We were. And it was one of those things that they kept on the news all the time, right? But that was probably one of the biggest, most devastating things. What caused it was not the source. What caused it was that it was too much river, too much flow. It overflowed all the banks, drowned everything. Excuse me. This throat's getting a little scratchy. So how would we take something like that and try to make it to where the Mississippi River did not flood extreme is if we had something like an overcurrent protection device, we'd be able to stop it before it even started. Otherwise, another way you would take care of it is create another path for the excess to go. Maybe carve something to the Grand Canyon. Go flood that sucker. Plenty of water area there for it to go to, right? I mean, you have what? 1,000 feet before, from the bottom to the top? Might shift a few boulders, though. So most circuits do have some form of overcurrent protection device, but it's not absolutely necessary. So a voltage source produces a difference in electrical potential or some form of pressure that's causing things to move. And that is what causes that current to move. Conductors have to carry that current. The load provides the opposition to the flow of current and creates work. Ohm's law states the relationship between a circuit's voltage, current, and resistance. The voltage is an electrical pressure. The unit is the volt. 1 volt of pressure will push 1 ampere of current through 1 ohm of resistance. By the way, anybody know how much resistance your body has? Actually, pretty good, especially if you've got skin. Any cuts or abrasions or anything, it actually drops. But yeah, our skin's pretty insulated. Excuse me. So current is the flow of electrons in a closed circuit. Unit is the amp. 1 amp equals 1 coulomb at 1 second. Resistance is the opposition to the flow of electrons. 1 ohm of resistance exists with 1 amp of current and 1 volt of push. And if you want electrical work, you have to have current. Excuse me. Okay. All right. So kind of a review from what we've already covered. You should be very familiar with this. Now, what does E stand for? Does anybody remember? We did go over this. Electromotive force. Electromotive force. The E is very typically used more for military or for textbooks. It's just how they refer to it. We typically refer to it as the volt because it is faster, easier to say, and it's something universally understood. Does that make sense? So when somebody sits there and says, you know, what is that? If you tell them that the voltage is, the electromotive force is 250 volts, they're going to look at you and go, what? The voltage is 250 volts. Much faster. Okay. So Ohm's law is the relationship between current, voltage, and resistance, and this is the primary formula. You remember, it's one we've done several times. And Ohm's law is about to really come into play with everything we do. So if you've not got it memorized yet, you might want to start memorizing. Okay. So what is the voltage for this particular problem? We have a current of 15 milliamps through a resistor with 1.8 mega ohms. Not really, because you're forgetting one big thing. Actually, two. It ain't just milliamps. That's mega ohms. Okay? That is milli and mega ohms, or milliamps and mega ohms. So the problem with that is what? We have milliamps and mega ohms. What does milli stand for? 10 to the what? 10 to the negative 3. What does mega stand for? 10 to the 6. So you have, if you translate this, you have 0.015 times 1800 with 3 more zeros behind it. So what does that give us? $27. Should be 27 kilovolts. Okay, it should be equal to 27 kilovolts. You're not dropping the zeros, you're turning them into the other meaning of them. Does that make sense? So you get 1.8 mega times 15 milli, you get 27 kilovolts. Does that make sense to everybody? Any questions? And yes, you will be expected on future tests and such to be giving me everything in this form of notation. Okay? All right. Go ahead and erase all the ink on screen. Everybody done with it, by the way, before I move on? All right. So you have the electromotive force of 15 milli times 1.8 mega gives you 27 kilovolts. This one, we're finding current. We have 27 kiloohms with 100 volts. Translated, that is 27,000 ohms versus 100 volts. So you should do 100 divided by 27 kilo, 27,000. Does that make sense? So what does that give me for current? We're looking for amps. What? Yes, I think so. Well, there is one thing I haven't showed y'all yet. I'll go ahead and show it to you now while you're thinking over this particular problem. And that is this. This is called the Ohm's Law wheel. The Ohm's Law calculating wheel. It's a very common, very common side of most electrical. What you're looking at here is you have your four sections of things you need to find. So let's say I'm looking for voltage. Let's say the only thing I've got is power and resistance. Well, look, I've got one right here. The square root of power times resistance will give me my voltage. If I simply have power and current, I can sit here and go, well, that's power divided by current. If I'm looking for current, let's say I have power and resistance, I've got the square root of power divided by resistance. Everything else is, yeah, essentially anytime you're trying to find current, you're dividing. Same thing for resistance. Anytime you're trying to find resistance, you're dividing. Yeah. So for resistance, if you're trying to find resistance with power and current, you have to square your current and you divide your power by your current. Square your voltage and divide by power, or voltage divided by current. Of these, the ones I would actually work to memorize is there's two elements here that you want to memorize. And that's finding current and finding voltage. Why? Because if I have current and I have voltage, I can find power or resistance with very little fuss and muss. Does that make sense? If I have either current or voltage, I can find my resistance or my power. So the main ones I might add to my repertoire of memorization are these two square root ones. So to find current, the square root of P divided by R. To find voltage, the square root of P times R. If you can remember those two along with your Ohm's law setups that I've given y'all, then you'll be a lot easier off to deal with all this. Does that make sense? Okay, any questions? I said I just figured I'd show y'all that, just kind of get y'all used to it. This is a very common thing. Like I said, all you have to do is type in Ohm's law wheel, and it pops this up. All right, so looking at this, we have our resistance and our voltage. What you should do is 100 divided by 27 kiloohms should give you 3.7 milliamps. Does that resonate with all y'all? So I'll just bring over this real quick. 100 divided by 27000 equals, and gives you this nice long number. But moving that decimal, 1, 2, 3, you get 3.7. If we're just kind of going close to home here. If you look behind that, that's just nothing but a 0. So you get 3.70 or 3.7 milli. How do I know it's milli? To get that one number in front of the decimal, you move it 3 times.
Well, I didn't. I did the exact same thing.
Okay, so there should be a fraction to decimal. There we go.
Oh, okay.
S to D.
Mm-hmm.
What that means is that's taking it from fraction to decimal, or decimal to fraction. If you press that a few times, it's going to keep moving it to different formats.
Right. Okay.
And that right there just put in engineering notation for you. Modern calculators are extremely convenient. All right. So we end up with a 3.7 milliamps. So what about resistance? We've got 30 milliamps and 15 volts. So that should be 15 volts. What am I dividing it by? What does 30 milliamps translate into? 0.03. You can even go so far as to put 0.030. That's how you end up with three numbers behind that decimal. Or moving that decimal in a run of 3. Okay? So what's my answer? Yep. 500 what? 500 ohms. 500 ohms. Everybody kind of get where we're going? All right. So what resistance will allow? All right, never mind. So V is equal to I times R, I is equal to V divided by R, and R is equal to V divided by I. Does that make sense? So if voltage constant, so this goes back to what we talked about the last time we really got into this, I think, particular set of slides. So voltage held constant, so voltage is not going to change. I and R sit on a seesaw. Okay? With voltage held constant, I and R are on a seesaw. Teeter-totter, whatever you want to call it. There's your voltage. You have I and R. So what does that mean? It means that as resistance increases, what's current going to do? It's going to decrease by the same amount. So if I double my resistance, my current will what? If I double my resistance, my current will be what? It'll be halved. If I double my resistance, my current will halve. If I double my current, my resistance will halve. Does that make sense? Because it's on a seesaw, one goes up, the other goes down. Does that make sense to everybody? All right. With current held constant, resistance and voltage tie together. So if one goes up, the other goes up. If one goes down, the other goes down. So instead of a seesaw, you just have an elevated plane with boxes on each side, and you want to keep this level, so every time you raise voltage, you're going to have to raise resistance. With I is constant, you want to keep them in balance. Does that make sense? Kind of, sort of? Nobody thinking I'm crazy so far? Nobody thinking I'm saying something that's not true? All right. So if I hold resistance as constant, again, it becomes true. When you increase voltage, you're going to increase your current by the same factor. So if I double voltage, I double current. If I half my current, I half my voltage. Does that make sense? Because you want to keep these balanced. You can also think of it as the reverse scenario. If you do not want to change your dam, right? If you're not going to change the size of the dam, then every time you get more push upriver, you're going to have more current going through that resistor, right? And every time things drop off, let's say we have a drought for a little while upstream, so that means you're going to have less push upstream, right? So my voltage went down, my current and my river are also going to what? They're going to go down, they're going to drop off. Does that make sense? All right, so what does it mean to be proportional? That means that two numbers, if a change in one becomes a change in the other. If something is directly proportional, as in voltage and current or voltage and resistance, when both numbers change in the same direction. If they're inversely proportional, like the relationship between current and resistance in this case, when one changes positively, the other one changes negatively. Does that make sense? Does that make sense to everybody? Everybody good? Anybody need a second? All right. So variables and constants, a lot of electrical equations consist of three terms. If the words directly or inversely proportional is used for two of the variables, the other one is considered a constant. I don't know why this is going so deep into this, but it is what it is. All right. Everybody good? So you have what's called linearly proportional. So resistance is directly proportional to voltage, inversely to current. Voltage is directly proportional to both, and currently is directly to voltage, inversely to resistance. So basically all three are saying the same thing I just said. Okay. All right, so in order to keep my resistance the same, in order to keep R the same, when I increase or decrease my voltage, what's happening to my current? My current will increase or decrease compared with my voltage. Does that make sense? So if my voltage goes up, my current goes up. If my voltage goes down, my current goes down. That is linearly proportional. Does that make sense to everybody? All right, so what is the value of I? Well, let's kind of all right, so I think we've kind of touched a little bit more on this than I was trying to get through tonight. All right, skip through some of this. So let's go on to energy and power, because I know y'all are, we've already covered Ohm's law quite a bit. So let's start talking about our next set, which is Watt's law. But energy and power, so energy is the fundamental capacity to do work. We have to have energy to go to work, right? So we get a good night's sleep every night so we can jump up the next morning, go to work, and be good, right? Be awesome. Energy is measured in joules, and power is the rate at which energy is used. It is measured in watts. Why? Because after the steam engine was invented, you had a gentleman named Gregory Watts who went and improved upon it. So it's named in his honor. All right, so power is equal to energy divided by time, and is equal to force times speed. One we're trying to look at is the relationship between current, voltage, and power in an electrical circuit. The primary formula is P is equal to voltage times current. Current is equal to power times voltage, and voltage is equal to power divided by current. It goes back to that, if you can find current and voltage in any circuit, you can find resistance or you can find power, or you can find both. Does that make sense? All right. All right. So the power in your, wherever you dwell, be it a house, apartment, townhouse, what have you. Power used over time or power consumption is given in watt hours. If you look at the power bill, the Alabama Power, or if you live on this side of Bessemer, I think you have TVA, Tennessee Valley Authority. Yes, they are a thing. Yes, they did initially start up in Tennessee. So you get your bill in kilowatt hours. A watt hour is found by multiplying the power used by the time. So in other words, that meter that sits outside your house that goes click, 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 click over all the power you use, that they use to try and calculate your power bill at the end of each month. The evil purple people eaters that use it make us pay a power bill. If we use 120 watts of power for 30 hours, we have 3,600 watt hours, or 3.6 kilowatt hours. This is literally how they come up with your power bill. Excuse me. Okay. So how do you reduce it, by the way? Anybody know? You can unplug everything before you go anywhere. You can kill the main circuit breaker, though I'm pretty sure all the food in your house would spoil. Technically, if you unplug everything, it is supposed to stop all that. Personally, I wonder if the lesser power bill is worth the extra effort you have to go through to unplug everything. Honestly, it's just kind of a question of you robbed Peter to pay Paul. So what was the point? You know, some people are really enthusiastic about it, but think about the work you have to do. You might be saving on power bill, but the work you have to do to go around and unplug everything to leave home, and then when you come home, you have to plug everything back up. Is it really worth saving a couple bucks? Yeah, if you're one of those people that tends to want to be, I won't say cheap, I'll say environmentally conscious, then yes, it is probably worth the reduction in bills and power consumption. It's always up to the person and individual. So one of the ways we produce work is producing through heat. Okay, heat is produced when you pass current through anything. Matter of fact, if you ever get near a power line, they tend to run pretty hot. That's why a working power line does not generally keep a bunch of snow on it unless it's extremely insulated. All right? I mean, it does not run hot, but it does not run cold. All right, so other power law formulas. So we already kind of covered these looking at the Ohm's law wheel. You can do I squared R, you can do V squared divided by R. But if you have voltage and current anyways, why don't you just multiply, divide, you can find what you need. So solving for voltage or current, again, it kind of go back to the two main ones I would recommend learning are this guy and this guy. Voltage is equal to the square root of power times current, or current is equal to the square root of power times power divided by resistance. It saves you a little bit of time. Okay? Hey, there's a giant Ohm's law wheel. So almost all electronic components are rated in something. Overcurrent protection devices are in volts and current. Conductors are in current and resistance per 1,000 feet. Incandescent light bulbs are voltage and watts. Insulators are rated in voltage and the environment. And it's actually is a really good way to kind of figure out what you're looking at sometimes. It's why if you look at your circuit breakers in your house, so something like your washer and dryer, what do they run? Voltage. What do they run? What does a hot water heater run as far as voltage? They run 220. They run 220 volts. The rest of your house, 99% of your house runs what? 120. Things like your stove, things like your hot water heater, or even your washer and dryer. So some of them have gone to 120. Most of them can still run 220, 240. So if you're looking at a circuit breaker and you're reading that it rates up to 220 volts and X amount of current, you might not be looking at the one for the plug that you're trying to mess with. You're probably looking at the one for your hot water heater or your stove. So it's good to kind of know that, right? Looking at your conductors, having that rated in current and resistance. What can that do for you? The less resistance, the more it can conduct. But the less resistance, it can also be more easily what? Overwhelmed and burned out, right? And matter of fact, that's kind of the biggest thing of why people stopped using fuses in houses. Why? Huh? It's not so much about the expense. When your house is wired, whenever the engineer that creates the wiring for your house, or the electrician that's supposed to know what they're doing, what are they supposed to do? Is that they are supposed to balance out the loads versus the conductors in your houses. So if you have, let's say, a 20 amp fuse to one circuit, then it was supposed to stay 20 amps and no more on that circuit. You can always go less, but you can't go more. So you're Joe homeowner. And so you've done a few improvements to your house. Why? Because heck, you felt like it and you felt like you know what you're doing. You decided to install a couple more lights. You decided to install another fan. You decided to install the big TV, things like that, right? But you have a problem. And the problem is every time you turn everything on, the fuse blows. Every time. Now, you're Joe homeowner. You don't know any better, right? So you keep replacing the fuse for a while, but after a while you're pissed off because it's expensive to replace that fuse, right? They're 50 bucks a pop. Why am I going to have to keep replacing this fuse? So I go down to the hardware store and I look at the guy behind the counter and I say, this fuse is a 20 amp fuse, but I don't want that anymore. What do I want? No. Because believe it or not, changing out the fuse box for the circuit breaker, that's a bigger pain in the rear. No, what you want is not that same fuse. You want a bigger fuse. You want a 25 to 30 amp fuse. Why? Because you're mad you've had to spend all this time, all this money going back and forth to the hardware store trying to get the right fuse. So you go for a bigger one. Now here's what you don't know, Joe homeowner. The wire in your house was rated for 20 amps. The wire in your home was rated for 20 amps, maybe 25. So you take your fuse home, you plug it in. You're not thinking about anything else because you're sitting there going, okay, I'm going to go watch sports on the TV. I'm going to turn on every light that's connected to this fuse. Your fuse is now a 30 amp fuse. The lines running to it only support 20 amps. Anybody else see the danger? So what you don't know is behind the walls, your insulation on your wires is melting. It's slow, but it happens over time. Eventually, it melts or burns away. what happens next? No. It's a 30 amp fuse. Your wire's only rated for 20. So what gives up first? Is it the wire or the fuse? It's the wire. Wire every time will give up. And then what happens next is it builds up enough heat, and you've got it against dry wood in your house, but you don't know what you've created behind that wall is a fire hazard. The reason we no longer install fuse boxes in homes is mainly for that reason. It's a fire trap waiting to happen. And that is, honest to God, the biggest problem with fuses. That's why we no longer use them, because a lot of people burned down their houses or caused minor fires in their houses because they didn't know what they were doing. Yep. That's exactly the fuses I'm talking about. That's why houses are no longer built like that, because the fuses were too easy, because you can just screw them in or unscrew them very easily if they're blown. And you're Joe homeowner, so guess what? Fuse keeps blowing. I'm tired of messing with it. You bypass the fuse or you go get a bigger one. And that has caused a lot of houses to be burned down or just burned. You know, just minor fires you might barely catch in time before it takes you out their whole house. Because most people don't routinely go up and kind of feel along the wall sometimes to see if there's hot spots. Because why would you? Do we ever think about the electrical in our house? No. Why would we? Do you ever think about the hot water heater in your house that you're supposed to service periodically? No, because, why would you? Things in your house are something that a lot of people don't pay attention to, and often it's too much regret. It's going to go out at the worst possible time, and generally it's the time when you're so tired and aggravated of dealing with it that you just make the bad mistake that you didn't know you made. So that's why you don't use fuses much anymore. You use fuses in electronics, and you use fuses in small things like control circuits and stuff. Circuit breakers are used for those same processes too. But you don't really see fuses used much in homes anymore. I think it's probably something insurance won't support much. A lot of homes to be brought up to code lately. I think if it's a house with fuses, you have to switch it to a circuit breaker. And you probably have to strip all the lines out of the house and redo them. Because if it's knob and tube, especially, which by the way, that's like one of the oldest wiring methods, you can look it up, that has to be replaced because generally it's not done very well. Incandescent light bulbs, we know those pretty well because we all go buy light bulbs periodically. You buy it, why what? A, what fits in the socket, B, the wattage, right? Because we like a little bit of power put out by these things so we can actually see the room we're in, right? And then, yeah. So resistors are rated in resistance and watts. And the ohm value is specified within a given tolerance. The tolerance is between kind of whatever that needs to be. It's always dependent upon what you buy it as. If it's under 2 watts, it's still on the resistor though. So that should look familiar. It's what we went over. Probably the last kind of stuff we went over in intro. All right. So power ratings is the power rating is the maximum amount of power that a resistor can dissipate without damage. Just like a light bulb. What is a light bulb rated? You put it in if you put a 30-watt light bulb in a 40-watt socket, what's it gonna do? It's gonna be kind of dim, right? Will it still work? Yeah. Work very well? Not so much. If you put a 40 and a 30, though, what are you gonna have? You have a bad bulb. You're gonna blow the bulb. Now, I don't mean you're gonna blow it up, but you're gonna blow out the bulb. You're gonna break the filament or whatever is inside it. Power rating is determined by the physical characteristics of the resistor. And the physical characteristics tend to be length, material, and circumference. So length, material, and width. Length, width, and material is probably the best way to say that. Okay? So basically size. So some general ratings. We have 1/8 watt, 1/4 watt, 1/2 watt, 1 watt, 2 watt. 1/8 of a watt is basically less than the size of your pinky nail. It's about half the size of your pinky nail. That's great in electronics. 1/4 watt's a lot of what y'all were working with the other day. 1/2 watt's a little bit bigger than that. 1 watt's pretty sizable. 2 watts, same. I used to have a card with them on it, but I don't at this time. So these are not to scale, but you kind of get the idea. Wire wound resistors have larger power ratings. Why? Because the more you add to it, the better it lasts for some reason. So it generally starts at 1 watt and goes up to 225. I keep dropping things. Dynamic braking resistors are some of them out there. I mean, if you've ever seen something that goes on, the most impressive ones I've come across are not very high in the resistance rating, but they are very high in the wattage rating. You can get kilowatt ratings on things like overhead cranes, because to start those motors up and then to start up the braking mechanism, you got to pull a lot of power on those things. And I have seen resistors seriously boxed in, but they're taller than me. Yep, they come that way. Electric water heaters and room heater elements can be as high as 6 kilowatts. Why? Because you don't want those filaments giving out, A, and B, because they're throwing a lot of heat out. Okay. Yeah, these are some of the ones that you can find out there. They can be really, really small, or they can be really, really big. Lower left, this one? Huh? No, that's a resistor bank. It's high wattage. It's gonna be a high wattage, but probably low resistance. Yeah. Something along the lines of that. So if you're selecting the proper resistor, you do not want to go too high, but you don't want to go too low. It's kind of that Goldilocks number, right? So calculated power, we have, let's see, 10 volts, 120 ohms. What's my current here? Those of you with calculators out. So that should be 10 divided by 120, yeah? What's my current? No, I don't think so. Other way around, hon. 10 divided by 120. So 83 83 milliwatts, right? Or, I'm sorry, 83 milliamps. Multiply that by 10 volts and you get 830 watts. Does that make sense? This one right here should be 10 volts as well, if I don't miss my guess. So you do 0.01 times 1,000 gives you what? 10 volts? Dang, I'm good. So 10 times 10, you'd end up with 100. I'm sorry, that should have been milliwatts. 830 milliwatts. This one should be 100 milliwatts. Now the smallest resistors only come as, let's say, 1/8 of a watt. What does that translate to? Should translate to 125 milliwatts. Now, will A or B go into 125 milliwatts? The answer would be B. You could use a 1/8 of a watt here. Could you use it in A? No, it'd be too small, right? Blow it out. Next, we can go up to a quarter watt, which is 250 milliwatts. That's still too small, right? I could technically use it for B, but it'd be too big, right? So it'd be a very dim light, right? The bulb's too big, you can't put enough power to light it. Does that make sense? We could go to a half watt, but that would be equivalent to 500 milli. And then that goes up to a 1 watt, which is exactly what it sounds like. So this guy right here would have to go up to the 1 watt, because if I put anything smaller in it, what is it going to do to it? It's going to fry it, right? Does that make sense to everybody? All right. So let's see. We got 14 slides left, guys, so I hope y'all can hang in there with me. We're almost done. And then next time we'll be able to move into series circuits. Yay! Move on to new material, right? So if I have 9 volts and 100 ohms with a quarter watt resistor, so these are 3 resistors here. We're looking for which one would be damaged. So I'll let y'all kind of take a look at that and work your circuits out. And let's see which one is damaged. Get y'all to do some math tonight.
I already know B is damaged
Why is that?
because you got too much resistance with small power.
By the way, just to help you out, see if you can get it a little bit more quickly. The formula for this particular run of problems is best done as P equals V squared divided by R. So what is my power at A? It's what? It's 810 milliwatts. So will my resistor here be damaged at only a quarter watt power?
Oh, I thought I said, yeah, it is. Do the math.
Yep, this guy right here is busted. For B, we have 24 volts and 1.5 kilo ohms. We have a half watt of power available to be used, and we have 384 milliwatts going through it. Will it be damaged? Nope. That one's good. And lastly, we have 5 volts and 10 ohms. Will this one be damaged? This one's 2.5 watts. What is our rating? As only 1 watt. So what's going to happen to this circuit? Because it's less than the wattage rating. Your half watt rating, okay, so light bulb, think light bulb, okay? If I have a socket that puts out, we'll say 30 watts maximum, puts out 30 watts, okay? I buy a light bulb that's 40 watts. The 40 watts is what it handles up to. If you surpass 40 watts, what would happen to that light bulb? It'd blow out, right? But if I put that 40 watts in a 30 watt socket, it would be fine, right? It would work. Does that make sense? That's kind of what you're doing here. This is the power that's actually moving through it. This is the power it takes. So you're trying to oversize, but not massively oversize. Because most of the circuits you're trying to deal with, most circuit boards, you're trying to make them small because you do not want to take up a lot of room. The original computer was the size of this room, right? And since then, we now have computers we wear on our wrist. Do you think those conductors are sized extremely high or extremely low? You want to try and get them to be low because you do not want to have a bigger watch on your hand, right? So that's the whole thing, is I want to size it just above my needs, right? So maybe for my 30 watt light bulb socket, you might want to get a 35 watt bulb or even a 40 watt bulb. Those bulbs would be safe in that socket. But you do not want to get a 30 bulb or less, because there you run the risk of the light bulb being blown. Does that make sense? All right. We'll call it today. Go ahead and kind of